Today I'd like to speak about the engineer Charles Cecil Sunderland of the John A. Roebling's Sons Company. Sunderland began working at Roebling's on October 15, 1901, just a few days before his 20th birthday. He retired on May 15, 1952, after 50 years and 7 months of continuous service. This brief talk will describe how, over the decades, and as he advanced to leadership positions, Sunderland sustained Roebling's engineering and manufacturing vitality by fostering research, developing new technologies, and manufacturing very high-quality products. The Roebling enterprise was, of course, founded by the patriarch, John Augustus Roebling, who was born and educated in Germany. Roebling immigrated to the U.S. in 1831 with the intent of establishing a utopian agrarian community in western Pennsylvania. But he soon began surveying and other engineering work. After observing the poor durability of hemp ropes on canal boat portage inclines, Roebling between 1839 and 1842 successfully developed technologies for making iron wire ropes, which were first used on the Allegheny Portage Railroad in western Pennsylvania. His first suspension structures were built between 1845 and 1850. In 1845, he built the Allegheny Aqueduct in Pittsburgh, Pennsylvania, and a year later he completed the Smithfield Street Bridge, also in Pittsburgh. Then between 1847 and 1850, he built 4 suspension aqueducts for the Delaware and Hudson Canal Company in eastern Pennsylvania. Therefore, he built 6 suspension bridges in just 5 years. Remarkably, Roebling developed 3 fundamental technologies that are still widely used today. The first is the in situ or in-place spinning of suspension cables. Second is the tight wrapping of suspension cables with wire. And lastly, he developed cable anchorages that are easily constructed, functional, and permanent. The basic cable spinning method devised by Roebling in 1845 is shown on this sketch. Roebling built 2 horizontal wood pulleys or sheaves about 10 feet in diameter on opposite sides of the river, about 1,100 feet apart. He then strung an iron wire clothesline or paternoster between them, with vertical supports spaced 340 feet apart. He attached 2 spinning wheels, as shown on the clothesline. Roebling pre-spliced and wound iron wire on large spools. He then placed wire on the wheel rim, held one end, and pulled the spinning wheel across by having a horse rotate the pulley, thus pulling a hairpin of wire across the river. The spinning wheel on the other side of the clothesline came back empty, but the process was repeated by rotating pulley in the opposite direction. Once the parallel wire cables were assembled, Roebling wrapped them tightly with wire using his patented machine. This method is still used today after 175 years. It is a very effective way of inhibiting corrosion of the wires and moderating differences in the temperatures of the wires when, say, one side of the cable is in the direct sunlight. In 1845, there was no standard method of anchoring cables. Roebling designed easily constructed, effective anchorages that proved to be enduring. His patented anchorage design featured a transition from wire cables to wrought iron eye bars outside of the anchorage, and a large cast iron plate for attaching end anchor bars. The wrought iron anchor bars were fully encased in protective hydraulic mortar to inhibit corrosion. He placed wooden mats at the base of the anchorage to engage the entire masonry mass to resist pullout and overturning. Roebling relied solely on the dead weight of the masonry block for anchorage. He did not rely on the strength of the surrounding soil. John Roebling died, unfortunately, in 1869 after an accident, but his sons, Washington, Charles, and Ferdinand, continued his legacy. Washington Roebling and his wife Emily completed the firm's great work, the Brooklyn Bridge, in 1883. Ferdinand managed financial aspects while Charles focused on improving production technologies. Edmund did not actively participate in the enterprise, and William died as a young boy. However, by 1918, both Ferdinand and Charles had died, and Washington was over 80 years old. Engineering leadership had to be provided by others, notably by Charles C. Sunderland. Sunderland was born in 1881 in the district of Northaram, County of York, near Halifax, United Kingdom. He immigrated to the U.S. as a 9-year-old boy in 1891. The family settled in Esopus on the Hudson River, about 75 miles north of New York City. None of his employment records or other papers I examined noted his education. It is possible that he was largely self-educated. Also unknown to me is why he came to seek work in Trenton, New Jersey. But in 1901, he was hired as a draftsman in the bridge and tramway department at Roebling's. By 1905, his title was that of an assistant engineer in a bridge and tramway department. And by 1910, at age 29, he was engineer in charge of the wire rope division. Surely one of the most important positions at Roebling's, because wire ropes were certainly their signature product. The basic component that Roebling produced was high-strength steel wire. Wires were then helically wound to make strands, which in turn were used to make wire rope, a very highly engineered product. Rope designs and rope-making machines were the purview of Charles Roebling. This is a patent for a specific type of wire rope filed late in his life in 1915 and only granted in the year of his death in 1918. One of the largest Roebling machines for making rope was about 60 feet tall and held 80 tons of spooled wire on its base. It has been designated a mechanical engineering landmark by the American Society of Mechanical Engineers. Since by 1910 Sunderland was the engineer in charge of the wire rope division, he must have worked very closely with Charles Roebling. In 1926, the year Washington Roebling died, the design of the George Washington Bridge over the Hudson River in New York City was finalized. The principal design engineers were Othmar Ammann, who was the chief engineer of the Port of New York Authority, Leon Moiseev, appointed as an advisory engineer on design for the Port Authority, and Alston Dana, appointed as engineer of design in charge of the design division, who had a staff of 30 engineers and draftsmen working under him. Both Dana and Moiseev have previous experience in suspension bridge design, but this was Ammann's first suspension bridge. The final design had a main span of 3,500 feet and an upper deck with 7 traffic lanes. A second deck for 4 projected rail lines was added only much later. There were 4 main suspension cables, each with a diameter of 36 inches. Charles C. Sunderland was responsible for preparing Roebling's bid for supplying the wire and anchorage steel and for erecting the cables of the George Washington Bridge. Roebling won the contract with a bid of $12,193,000, which was about 40% of the total cost of the bridge proper. Sunderland was appointed Roebling's chief engineer for the execution of the George Washington Bridge contract. The scale of the work that Roebling had to complete was unprecedented and daunting. This is a table prepared by Sunderland comparing the 6 largest existing suspension bridges with the George Washington Bridge. The most striking fact is that the George Washington Bridge was designed to have a main span of 3,500 feet, twice as long as the previous longest span, which was 1,750 feet of the Delaware River or the Benjamin Franklin Bridge in Philadelphia. The total weight of the wires in the main cables of the George Washington Bridge, 28,500 tons, was greater than the combined weight of all the cables of the 6 largest suspension bridges built to date. The suspender ropes had the largest diameter ever used on a suspension bridge. The ropes were sophisticated assemblies. The 2 7/8 inch diameter ropes had 283 wires of 10 different sizes that made up the rope. Wire ropes have an irreversible stretch from compaction when an applied load exceeds the tension used during manufacturing. This makes the lengths of the ropes in service uncertain. To eliminate this uncertainty, Sunderland built a pre-stretcher at Roebling's Kincora plant. The pre-stretcher was an 1,875-foot long bed with a fixed reaction block at one end and hydraulic cylinders at the other end that stretched ropes to 125% of their expected service load. This made it possible to know their exact lengths when in service. Moreover, the pre-stretching increased the stiffness of the ropes or the force required to produce any given stretch. The image shows that the moving end had a large sheave or pulley so that ropes as long as 3,750 feet could be pre-stretched. The strength of such large ropes could not be determined with any available equipment. Therefore, Sunderland commissioned a testing machine that could apply 2,500,000 pounds of force, greater than the capacity of all previous testing machines. It is amusing to read test descriptions which describe the anxiety at hearing the first wire failure and the retort and the building vibrations produced when a wire rope finally broke. Building a bed that could pre-stretch a 3,750-foot long rope was necessary because the ropes were first used to support footbridges, which were about 3,560 feet long. The ropes are shown in the highlighted area in the bottom left image. The drawing on the right shows a fully assembled main suspension cable and a partial cable during assembly. Each circle represents a strand or a bundle of 434 wires. The strands were arranged in a hexagonal shape with one of the sides in the horizontal position. Long wire lengths were obtained by splicing. Sunderland carried out a rigorous testing to verify the capacity of the wire splices. Almost 12,000 tests of splices were performed, which indicated that they, on average, developed 98% of the strength of the wire. Splices were made by deforming the ends of the wires and then pressing or swaging 2.5-inch long sleeves, a quick, elegant, effective process devised by Roebling. The wire spinning process, although it still used the wheels conceived by John Roebling, was much, much more sophisticated in its control and rate of placement. This is a drawing from the Transactions of the American Society of Civil Engineers. The actual operation is difficult to describe, but in chapter 24 of Hamilton Schuyler's 1931 book, The Roeblings, Sunderland, who wrote the chapter, listed 16 features of the cable spinning process that were developed specifically for the George Washington Bridge. Sunderland stated that they were, quote, the result of 2 years' scientific and mechanical investigation in the laboratories of the Roebling Company, unquote. After 434 wires were spun, they were combined into a strand. A strand was precisely placed within a hexagonal pattern over the saddles, while at the anchorages, a strand loop went over shoes, as shown in the highlighted area on the bottom right. The shoes were attached to eye bars, which were embedded into the concrete of the anchorage. After all the 61 strands for a cable were assembled, the cable was compacted into a circular shape and then wrapped with wire, as John Roebling did. The weight of the footbridges was then transferred to the main cables, and the wire warps were repurposed to serve as the suspenders for the deck. Note that because of the known stiffness of the pre-stretched ropes, they could be cut to precise lengths, and simple, elegant swage connections could be used to support the floor girders. Adjustable turnbuckles were not needed. Sunderland and his staff of Roebling engineers and ironworkers achieved what was thought to be impossible. Sunderland succinctly observed, according to the contract, one set of 2 cables was to be finished by December 1st, 1930, and a second set of 2 cables was to be completed by December 1st, 1931. Due to the developed improvements by the Roebling Company, it was possible to complete all cables ready for the erection of the steel suspended structure on October 28, 1930. That is, the first set of cables was finished over a month ahead of contract, and at the same time, the second set was completed, 13 months ahead of contract requirements. The record of constructing in position of 56 million pounds of bridge wire in a period of 294 calendar days will not be exceeded for some time to come. With Sunderland's leadership, the Roebling Company's achievement allowed the opening of the bridge for vehicular traffic on October 25, 1931, about 8 months ahead of the original schedule. Othmar Ammann, the chief engineer of the Port Authority of New York, wrote a letter to the Roebling Company and Sunderland stating his appreciation. Sunderland, it reads in part, "I take this occasion to express to you, on behalf of the engineering staff of the Port Authority, its appreciation of the excellent and efficient manner in which you have carried out this unusual and important work, and in particular also the cooperation which you and your engineering staff have manifested throughout the period of construction." This was a truly effusive praise from the very reserved Swiss Ammann. On the group photo of the Roebling staff shown at left, Sunderland is barely visible, holding his hat, standing next to the Roebling superintendent, Howard Hills. The availability of Sunderland's pre-stretcher at Kincora had an immediate effect on the design of medium-span suspension bridges. The eminent bridge designer David Steinman built 2 medium-span suspension bridges at the time the George Washington Bridge was being erected, the Grand Mare Bridge in Quebec and the St. John's Bridge in Oregon. Steinman realized that Roebling's ability to fabricate very long lengths of strand to a very precise length tolerance meant that main suspension cables could be formed by simply bundling pre-cut, pre-socketed Roebling strands, precluding the need for cable spinning. For the Grand Mare Bridge, Steinman used 37 pre-stretched, shop-socketed bridge strand manufactured by Roebling. Each 1,680-foot strand had to meet a length tolerance of plus or minus a half an inch. For the St. John's Bridge, Steinman used 91 bridge strand. Each 2,720-foot strand had to meet a length tolerance of plus or minus 1 inch, a seemingly impossible feat. Another great advantage of pre-socketed strands is that they greatly simplified the connection to the anchorage bars. By the early 1930s, the Roebling Company not only manufactured unique wire ropes, strands, and end connections, but they also had the engineering and construction expertise to design and erect suspension bridges. However, Roebling leadership evidently elected not to compete with U.S. consulting engineers for U.S. commissions because the consulting engineers were also potential customers for Roebling's manufactured products. Roebling did compete for commissions outside the U.S. One example is the San Rafael Bridge in the Dominican Republic. This bridge was designed and completely prefabricated in Trenton, New Jersey, and then erected by the Roebling Company under direct contract with the Dominican government. Sunderland used 9 pre-stretched, pre-socketed bridge strands, but he did not bundle them and wrap them with wire. Rather, he decided to leave them in an open, parallel arrangement, relying on the galvanizing of the individual wires for corrosion protection. Sunderland espoused this philosophy for subsequent medium-span suspension and other types of bridges. Trenton is close to Princeton, New Jersey. This proximity naturally led to collaborations between Roebling engineers and structural engineering students and professors at Princeton. In 1930, at the time of the erection of the George Washington Bridge, a conference was held in Princeton to determine if physical models could be used for final design of suspension bridges. It was attended by practically all the prominent U.S. suspension bridge designers whom I've highlighted with red ovals. As usual, most of the work was done by a bright undergraduate student named Blair Birdsall under the supervision of Professor George Beggs. In the photo, Charles Sunderland is in the front row, second from left. Birdsall is in the back row, last row, third from left. Aman also attended the conference, but chose not to be in the group photo, so I've added his image on the right-hand side. The observations from the experimental work were summarized in a paper written by Beggs, Timbley, and Birdsall. The principal conclusion was that it appears practicable to resort to physical model analysis for the design of suspension bridges of novel but useful types too difficult for mathematical analysis. But most importantly, Blair Birdsall joined the Roebling Company in 1934, bringing expertise and a disposition toward the use of physical models for design of innovative systems. Over an 18-year collaboration, Sunderland and Birdsall truly bonded as mentor and protege. It was Birdsall's extreme good fortune that Roebling won the contract to supply the wire and erect the main cables of the fabled Golden Gate Bridge, and that he was assigned to work on the erection of the cables. Blair Birdsall noted that in preparation for work on the Golden Gate Bridge, the then chief engineer of the Roebling Bridge Division, Charles C. Sunderland, developed a much improved scheme for cable construction. The drawing compares the cable construction at the saddles of the George Washington Bridge and of the Golden Gate Bridge. For the George Washington Bridge, Sunderland used uniformly sized strands with 434 wires, layered horizontally with the hexagon side at the base of the saddle. For the Golden Gate Bridge, Sunderland used strands of sizes varying from 256 to 472 wires. He stacked the strands in vertical columns with a hexagon apex at the base of the saddle. The Golden Gate arrangement had two important advantages. Vertical stacking made the temperature of the strands much more uniform along the span, and both the vertical arrangement and the variation of strand sizes allowed a much more efficient compaction of the cable. The George Washington Bridge cables had 22% voids, whereas the Golden Gate cables have only 17% voids. These advantages were significant, and the technology was widely diffused internationally. Here are statements from two late 20th century prominent British and Japanese suspension bridge designers. All the major British suspension bridges have main cables that are of the built in situ parallel wire type pioneered in the USA by John A. Roebling. Subsequently, British contractors have been able to act on their own, but the system used has always been essentially Roebling, with the strands set in a vertical rather than a horizontal hexagonal form. Dr. William C. Brown, partner of Freeman Fox and Partners. Because of the good experience with Roebling strand arrangement in a Kanmon bridge, all the cable arrangements of bridges under the Honshi Bridge project were designed with a vertical hexagon apex, Ichiro Konishi. But after the euphoria of the great design and construction successes of the George Washington and Golden Gate bridges, American engineers received a blunt lesson. The Tacoma Narrows Bridge collapsed in a windstorm on November 7, 1940. The film of Galloping Gertie tearing itself apart has been seen by practically everyone. The failure occurred because design engineers did not understand the dynamic forces caused by wind, nor how to design a deck to limit dynamic responses. Of course, several investigative bodies were formed. The most prominent was convened by the American Institute of Steel Construction and the Public Roads Administration. Sunderland and Birdsall were members, and the Roebling Company heavily subsidized the cost of board activities. But after December 1941, the nation was focused on the war effort. The scope of Roebling expertise on suspension bridges in the early 1940s is illustrated by the Peace River Bridge of the Alaska Highway in British Columbia. The highway was then considered an important military route. The elevation shows that the bridge had a main span of 930 feet and an overall length of 2,130 feet. Roebling was authorized to proceed with the superstructure on November 23, 1942, and the bridge opened to military traffic on August 4, 1943. Roebling fabricated all superstructure components in Trenton, shipped them 3,000 miles, and erected the bridge in less than 8 months. The design showcased Roebling features and Roebling products. The main cables consisted of 24 pre-stretched, pre-socketed, galvanized 1 7/8" diameter bridge strands arranged in an open array as advocated by Sunderland. The prefabricated strands were hauled over the river by a continuous 1-inch diameter hauling rope. Unfortunately, the tower foundations were not adequately protected, and by 1955 the river had severely scoured the foundations. And in 1957, a leak in a water main caused movement of the north anchorage and eventual collapse of the bridge. In June 1944, Roebling received a contract from the U.S. Army to design a suspension bridge of 600-foot span that could carry Army tanks. Because of the collapse of the Tacoma Narrows Bridge, Sunderland had already considered alternate ways of stiffening suspension bridges and had conceptualized a new form called a cable truss. The system devised by Sunderland did not rely on a bridge deck to augment the stiffness of a suspension bridge. Rather, it was a truss-like system, but with all tension or cable members. Its stiffness was increased by tensioning the bottom cord, which increased the tensile forces in the members and thus their stiffness. However, Sunderland's cable truss was very difficult to analyze mathematically. Therefore, Birdsall and Sunderland built a 1/10 scale physical model and predicted behavior of the full-scale bridge from measurements of model responses. The image on the left shows model vehicles, presumably models of tanks, traversing the model bridge. Because the war ended before the research was completed, the U.S. Army canceled the contract, and a full-scale prototype bridge was never built in the United States. This is a Roebling publicity photo showing Birdsall and Sunderland pretending to be taking readings from the model. In 1948, the Roebling Company won a contract to design and build a bridge over the Rio Lempa, near the town of San Marcos in El Salvador. Sunderland and Birdsall decided to design, fabricate, and erect their first cable truss bridge. It was a 5-span bridge with a total length of 2,550 feet. The deck and longitudinal girder were very slender because they were not designed to increase stiffness. The bridge was completely prefabricated in Trenton and shipped to El Salvador. Following Sunderland's philosophy, the top cord consisted of an open array of 24 pre-stretched, pre-socketed, galvanized bridge strands, very similar to the arrangement used for the Peace River Bridge. The lower cord was also an open array of 8 strands, post-tension to produce tension in all the diagonals and to increase the stiffness of the cable truss. The right-hand drawing shows that the tension in the lower cord was equilibrated by placing the concrete deck in compression. The San Marcos Bridge was certainly one of the most innovative bridges built in the mid-20th century. It was uniquely a Roebling achievement, with a design based on their experimental research, with Roebling wire strands and end connections, and with many unique Roebling steel forgings and castings. No other manufacturer or consulting engineering firm in the world had the breadth of engineering knowledge, manufacturing capabilities, and construction expertise to conceive and execute such a design. But Sunderland always prioritized the Roebling Company as a manufacturer, financially dependent on selling wire products, which meant anticipating and creating markets for their products. Therefore, in 1944, Sunderland also began research on prestressed concrete and later collaborated with Leo Koff, a British engineer who immigrated to the United States. Prestressing concrete and compression minimizes cracking and hence increases the stiffness of reinforced concrete products. Prestressing concrete is effective in the long term only if very high strength steel is used. The technology was pioneered in Europe in the 1920s, and European engineers and builders had the most experience. However, Sunderland knew that Roebling wire, rope, strand, and anchorage products were as good or better than those available in Europe. Moreover, Roebling had a unique experience with prestressing steel structures, as exemplified by the San Marcos Bridge. Therefore, following Sunderland and Birdsall's traditional research methodology, they began by building a model structure. It was a 20-foot long model, proportioned to be a 1/10 scale model of a 200-foot long bridge. The model consisted of 5 4-foot long precast concrete sections, post-tensioned together with 10 parabolic galvanized aircraft cables 5/16 of an inch in diameter. The model was similar to beams proposed earlier by Dischinger and Finsterwalder in Germany. However, Sunderland and Birdsall had a definite objective. They sought to determine if time-dependent strains in a concrete caused significant losses in the prestress forces and large increases in displacements under a constant load. Measurements over 3 years indicated that a permanent state of prestress can be achieved with no measurable increases in displacements after the first year. Concurrently, Sunderland, Birdsall, and Koth thought of potential applications of post-tension concrete. One of their ideas was that post-tensioning could be used to achieve crack-free concrete airport runways. As a proof of concept, Roebling built a section of their Cicero, Illinois warehouse floor as shown in the drawing. An unreinforced slab, 9 inches thick, was cast on sand. A layer of paraffin wax was applied, and then a 3-inch thick top slab was poured. In October 1946, the top slab was post-tensioned in 2 directions, inducing a compressive stress of about 700 pounds per square inch in the concrete. The concept was that the pre-stressed slab would float over the base slab and remain uncracked. The former Roebling warehouse exists and is currently a self-storage facility. In 2007, the parts of the floor that were visible were crack-free. The floor is without doubt the oldest pre-stressed floor system in the United States. Sunderland used post-tension modular concrete floors for other Roebling-designed bridges. The floor of Roebling's Lumberville pedestrian bridge over the Delaware River was precast using 4-foot by 9-foot modules and then post-tension in 2 directions. This was a relatively small job, but it was surely done as a marketing demonstration of the potential of pre-stressed concrete and the usefulness of Roebling products. Another bridge designed, fabricated, and erected by Roebling was the Rio Paz suspension bridge between Guatemala and El Salvador, completed in 1949. The Sunderland-type main cable, consisting of an open array of bridge strands, the bolted plates for connecting the suspenders, and the socketed suspenders are all distinctly Roebling features. The floor of the bridge was precast in 21-inch by 21 feet 7-inch modules. The modules were then post-tensioned along their lengths and then post-tensioned together longitudinally. The Rio Paz bridge is extant, but I am uncertain whether the deck is still the original one. The first great opportunity for Roebling to showcase its capabilities in pre-stressed concrete in the United States came from the city of Philadelphia, downriver from Trenton. The city needed to replace a bridge to carry Walnut Lane over Lincoln Drive and Monoshiny Creek. After 2 bids for stone-faced concrete arches exceeded the budget, the city in 1947 indicated a willingness to consider pre-stressed concrete bridge proposal. The first proposal for a pre-stressed concrete bridge on Walnut Lane in Philadelphia was made by Leo Koth, Charles Sunderland, and a John A. Roebling Sons Company. This is a rendering of the Koth-Sunderland-Roebling proposal, which featured haunched continuous girders. Some structural details of design are given by these drawings. There are 3 box girders with a variable depth and continuous draped pre-stressing ropes. It is astonishingly advanced design that would be considered modern if built and designed today. It features all the Sunderland principles. Post-tensioning, meaning that the concrete is cast first, cured, and then pre-stressed. Large galvanized tendons, continuous tendons, unbonded tendons, accessible for inspection, and compact swaged anchorages. Regrettably, the Sunderland Roebling design was perhaps too advanced. The city of Philadelphia selected the design of Professor Gustave Manuel, a well-known Belgian engineer in prestressed concrete who had made a later proposal in April 1948. Sunderland did not object to the award, consistent with his prioritization of the Roebling Company as a manufacturer of wire products. But Manuel, in fact, chose to use Roebling's high-strength ungalvanized cold-drawn wire for the Walnut Lane Bridge, which was arguably better than any European product. Manuel's Walnut Lane Bridge opened to traffic on February 1, 1951, and is traditionally considered the first prestressed concrete bridge in the United States. Despite Sunderland's disappointment, Roebling post-tensioning systems inspired several other pioneers in prestressed concrete. Ross Bryan in Tennessee and C.L. Johnson in Michigan built block bridges using Roebling post-tensioning products. These early bridges were built at the same time as the Walnut Lane Bridge, but received much less publicity and much less recognition. Because Sunderland began research on prestressed concrete in 1944, by the early 1950s, Roebling produced a variety of products for the prestressed concrete industry. Roebling produced strands up to 1 11/16 inches in diameter for design loads up to 280,000 pounds, and corresponding compact end fittings that were certified to carry the design load. But the real fruition of Sunderland's vision of post-tension concrete bridges with unbonded, galvanized, accessible tendons was realized not in the U.S. but abroad, in Cuba, shortly after his retirement and death in 1952. 5 post-tension bridges were designed and built in Cuba using Roebling post-tensioning technology in collaboration with Luis Sáenz, Mario Suarez, and Jose Marti. They are the Canas River Bridge of 1952, the Agabama Bridge of 1953, the Arimao and Cuyaguateje bridges built in 1954, and the Felipe Pazos Bridge of 1956. The Canas River Bridge had a central span of 250 feet, and the tendons were draped to increase their efficiency. The strands were galvanized and coated with bituminous paint to minimize corrosion. The highlighted note underscores Sunderland's philosophy. It states in part, "The strands are readily accessible for inspection, and one or more could easily be replaced if it should ever become necessary." The Cuyaguateje Bridge extended the main span to 300 feet with a variable box girder depth, improving both the appearance and the structural efficiency. The drawing shown depicts a bridge similar to the Felipe Pazos Bridge with 3 equal spans of approximately 153 feet. The end fittings are classic Roebling products. In summary, Charles Sunderland, the John A. Roebling Sons Company, together with consulting engineer Leo Koff, developed a complete American concrete post-tensioning technology from 1944 to 1952. This included high-strength, stress-relieved 7-wire strand, high-strength, large-diameter galvanized and pre-stretched strands and ropes, compact, swaged anchorage systems, and box girder bridge designs with accessible, unbonded, large-diameter continuous tendons. The extant post-tension bridges in Cuba are strong vindication of the Sunderland Roebling Koff approach or philosophy to corrosion protection. Sunderland's legacy is perhaps best appreciated by his peers. These are a few testimonials to his character, vision, and engineering contributions. On main cables of suspension bridges, in preparation for work on the Golden Gate Bridge, the then chief engineer of the Roebling Bridge Division, Charles C. Sunderland, developed a much improved scheme for cable construction. the genius of the man responsible for the cables of the longest spans in the world. On cable truss suspension bridges, the main features of the superstructure design were conceived and developed by the late Charles C. Sunderland, former chief engineer of the Bridge Division. The El Salvador Bridge is a memorial to his vision and genius. On pre-stressed and post-tension concrete, it is understandable that the great Charles C. Sunderland would follow the example set by the Roeblings. Thanks to the vision of Mr. Sunderland, we started development work on adapting the principles of pre-stressed concrete to American practice in 1944, and by the time these principles became sufficiently recognized in this country to begin to produce a market for wire, we were thoroughly entrenched as one of the recognized authorities in the field. Our only regret is that one of the grand pioneers, our former chief at the Roebling Company, boss Sonny Sunderland, cannot be present to view with satisfaction the fruits of his vision. Thank you.